All right, this is going to be a quick pre-lab because it builds off the other, but there are still a few things we need to define. The terms that you need to be familiar with is temperature. Now, I know some of you are coming from various places for your lecture, so you may not have had temperature defined to you before. So I'm going to define temperature right now. Temperature is the average kinetic energy of a group of particles. There are two really important parts to this definition. The first of all, temperature is the average of kinetic energy. So temperature is directly related to the motion of molecules. The second part of this definition that's really important is the fact that temperature is an average. To explain why this is important, I want to quickly define a term that you may or may not be familiar with, and that's heat. Heat is a quantity of energy that flows due to differences in temperature. The classic way I like to explain the difference between heat and temperature and help you understand why the fact that temperature is an average is important is to use this analogy. We've all had that one idiot friend at a party who takes a match and they like to light it, and then they hold their hand over the flame and say, "Oh, look, it's not burning my hand. Hurt." Right? We've all seen that guy. You're saying, "No, Dr. Kelly, we apparently have a better quality of friend than you do." Okay, that having been said, we've seen people light a match, hold their hand above the match, and not get burned. Well, that match head is burning at around 700 degrees Celsius. A really, really high temperature. In contrast, what would happen if you were to stand in the middle of a bonfire? If you stood in the middle of a bonfire, you'd be doing your Joan of Arc impersonation, right? You'd get seriously hurt if you stood in the middle of a bonfire. Well, wood, or that bonfire flame, that's only around 300 degrees Celsius, a good 400 degrees lower than your match. So why in the world does somebody get damage due to a wood fire at 300 degrees Celsius, but not at the match at 700 degrees Celsius? It's because temperature is an average. Even though each molecule in this match head has a higher average degree of kinetic energy than the molecules of the wood, because there's fewer molecules in the match head, it's putting off less heat. This bonfire, there's a whole lot more molecules. So even though each molecule has a lower average, it has more heat. So that's the difference between temperature and temperature and heat. temperature is an average. Another reason that it's important to think about temperature is, well, I'm going to go more directions I don't need to go for the lab at the moment. But temperature is the average of the kinetic energy of a group of particles. The next couple terms we want to define are freezing point and the freezing point is the temperature The freezing point is the temperature at which a liquid goes into the solid phase. The melting point is the temperature at which the liquid goes into the solid. I got that second one backwards. I did that on purpose to make sure you guys were paying attention. Congratulations if you were. Great, my professor just messed up the melting point definition. I wonder if he forgot to mail in one of his box tops off the cereal box when he got his PhD. But at any rate, I didn't. I mailed in all 5 and my check for $2.99, and they sent me a cool certificate. But at any rate, the freezing point is the temperature at which a liquid goes into the solid phase. The melting point is the temperature at which the solid goes into the liquid phase. One other definition that's a review, and that's the definition of internal energy. Remember, we defined internal energy as the sum of the potential We defined internal energy as the sum of the potential and kinetic energies that make up a system. So internal energy is the sum of the potential and kinetic energies that make up our system. So what I want to ponder now is the relationship between temperature and internal energy. If the temperature if the temperature of our system changes, and temperature is the average kinetic energy of our system, then a change in temperature must equate to a change in internal energy. Not only that, but the two must be directly related. If the temperature of our system increases, then we must see an increase in the kinetic energy of our system. What we're going to be pondering, and something I want you to think about, and I'm not going to tell you the answer right away, what if we add energy to a system and the temperature doesn't change? Well, energy can't be created or destroyed, right? So that energy has to be going somewhere. Since the temperature's not changing, we know that the internal kinetic energy can't be changing. So what must be changing? Remember, internal energy is the sum of the kinetic and potential energy of our system. And if you remember from last lecture, where do we see potential energy? We see it in chemical bonds, and we see it in the position of atoms and molecules inside a substance. One more thing to ponder, and as you think through this on your own, let's take a look at ice. All right, so I've drawn my ice molecule here. Inside my solid ice molecule, my molecules of water are held firmly in place. They can't really move. They're held in place by intermolecular forces. And I don't really want to go into intermolecular forces for right now. They're just a force of attraction. Between two molecules. They're almost like a bond. They're not, your molecules aren't married like the atoms in a molecule. Your molecules are just sort of having a casual relationship with each other, right? They're locked into place. They're not really looking for other molecules, but they're not official, right? So this intermolecular force holds them in place. This intermolecular force is an area of strength. It's a bond between them. In order to overcome this intermolecular force, it takes energy to break that intermolecular force that holds the ice molecules into place. That requires energy. When water leaves the ice phase and enters the liquid phase, what's happened is those intermolecular forces have become much weaker. One of the molecules has gotten a little bit braver and decided it wants to move around and see other water molecules. Not only that, but you can sort of think of it as it's wanting to play the field. So we had to add energy to weaken intermolecular forces to move from a liquid to a solid. Here, the intermolecular forces are still present, but they're much weaker. Now, if we're going to go from a liquid to a gas, in a gas, our molecules have no attraction for each other whatsoever. They change their position even greater than, and they change the molecules they're seeing even more than they do in a gas. Matter of fact, compared to a liquid, these intermolecular forces are broken altogether. So all the energy stored in those intermolecular forces has to be overcome. It takes energy to overcome these intermolecular forces. When you boil a liquid, or when you melt ice, it is going to require energy And that's all I'm going to say. And I want to see if you can extrapolate in your post-lab questions based on your lab results a couple things that you think is happening when you look at your heating curve and your cooling curve of water freezing and melting. All right, that's it. Oh, I should have really had you write down a word. Why don't you write down Robin? Everybody write down Robin.